Hello everybody, and welcome to this video on writing ionic equations. Now, if you have read up on this chapter, you would know that an ionic equation basically shows us what actually goes on inside a chemical reaction. Now, I have two diagrams here, one showing lead-2 nitrate dissolved in water, and you see that it forms Pb2 plus ions and NO3 minus ions. On the right hand side, I have potassium iodide dissolved in water, and it forms K plus and I minus ions. Now, when I mix these two solutions together, they will form a yellow precipitate known as lead-2 iodide. Now, if you recall in semester 1, when you did assignment 3, this is the reaction that you carried out. Now, how do we construct an ionic equation? Now, first of all, you should write out the chemical equation, or the balanced chemical equation with the state symbols. Secondly, you've got to identify all the aqueous compounds in both the reactants as well as the products. In this case, we see that lead-2 nitrate is aqueous, potassium iodide is aqueous, and potassium nitrate is aqueous. Now, for these aqueous compounds, as you have seen in the diagrams above, they split into their corresponding ions. And this is what we should write out in the total ionic equation. What do I mean? So let's take a look at lead-2 nitrate. Lead-2 nitrate consists of Pb2 plus ions in the aqueous state and 2 nitrate ions also in the aqueous state. Right? Next, let's take a look at potassium iodide. Potassium iodide splits into K plus and I minus, right? But because of the stoichiometric ratio here, it will form 2 K plus AQ as well as 2 I minus AQ. And that's it for the reactants. Now let's take a look at the products. For the products, if we take a look at PbI2, it is a solid. It does not dissociate in water, therefore it will remain as PbI2 solid in the ionic equation. Now, for potassium nitrate, it is an aqueous compound, therefore it will dissociate to form 2K plus aqueous and 2 nitrate ions aqueous. And this is your total ionic equation. Now, at this point in time, I want to introduce this term to you called spectator ions. Now, what are spectator ions? Now, try visualizing, or maybe I can help you visualize, a football match. Now, at a football match, there are usually a lot of spectators, right? But no matter how many spectators there are, or whatever the spectators do, it does not affect the outcome of the match. What do the spectators do? They just sit by the side and they watch the match happen. They do not take part in the match. Alright, I repeat, the spectators in a match, they sit by the side, they do not take part in the match, alright, and they do not play a role in the outcome of the match. Right? They just sit by the side and watch. Nothing happens to these spectators. Now, how does this apply to writing an ionic equation? Now, in the total ionic equation, there are also spectator ions. Why do we call them spectator ions? Because at the beginning of the reaction and at the end of the reaction, there is no change to these ions. Therefore, we call them spectator ions. Now, how do we identify spectator ions? Now, let's take a look at the total ionic equation again. Now, let's look at the reactants highlighted in purple and compare it to the products highlighted in green. Now, let's look at each ion in the reactants one by one, and we will see whether it appears in the products or not. Firstly, let's look at lead. Pb2 plus appears in the reactants highlighted in purple, but does not appear as Pb2 plus in the products highlighted in green. Therefore, it is not a spectator ion. For nitrate, NO3 minus AQ appears in the reactants. It also appears in the products. Therefore, before and after, there is no change. There is no change to the nitrate ions. Therefore, it is a spectator ion and it can be cancelled out. Next, let's look at the potassium ions, K+. Now, for K+, we see it in the reactants. We also see it in the products. Therefore, it is a spectator ion and it can be cancelled out. Lastly, for iodide, iodide appears in the reactants but does not appear as iodide in the products. Therefore, it is not a spectator ion. So therefore, our net ionic equation will just be Pb2 plus AQ plus 2I minus AQ to give you PbI2 solid. This is your net ionic equation. Now let's take a look at another example. Now in this case, we are looking at a neutralization reaction, reaction between an acid, which in this case is sulfuric acid, reacting with sodium hydroxide, NaOH. Now again, remember, the first step we have to do after constructing the balanced chemical equation is to identify the aqueous species. Now, sulfuric acid is an aqueous compound. Sodium hydroxide is an aqueous compound. Sodium sulfate is an aqueous compound. So therefore, for these three compounds, we will split them up into their corresponding ions. Now let's take a look first at sulfuric acid. Sulfuric acid releases H+, AQ. But remember, this is H2SO4, therefore coefficient should be 2. It also releases a sulfate ion. Next, for sodium hydroxide, remember the coefficient here is 2. So therefore it will release 2 Na plus AQ plus 2 OH minus AQ and that's it for the reactants. Now let's take a look at the products. For the products, here we have sodium sulfate. Now remember, this is Na2SO4, so therefore it will release 2 sodium ions and 1 sulfate ion. Next, we have water, but water here is in the liquid state, not in the aqueous. It is in the liquid state. Therefore, it will not be split up, and we will keep it as 2H2O liquid. Alright? So, now that we have this total ionic equation, let us now try to identify the spectator ions in the total ionic equation. So again, we will look at the reactants highlighted in purple and contrast it to the products highlighted in green. So let's go one by one in the reactants. First, let's take a look at H+. H+ appears in the reactants, but in the products, it does not. There is no H+ in the products. Therefore, it is not a spectator ion. Next, let's look at sulfate. Sulfate appears in the reactants. It also appears in the products. So therefore, this is a spectator ion. Right? It remains unchanged. Therefore, it can be cancelled out. Next, let's look at sodium. Sodium ions appear in the reactants. They also appear in the products. Therefore, it is a spectator ion. It can be cancelled out. Lastly, for the hydroxide ions, OH minus AQ appears in the reactants, but not in the products. Therefore, it is not a spectator ion, and it cannot be cancelled out. So therefore, our net ionic equation can be written as 2H plus AQ plus 2OH minus AQ to give you 2H2O liquid. Now, as you might have noticed, they all have the same stoichiometric coefficient, so that can be simplified. We can cancel this out to give you H plus OH minus to give you H2O liquid. And this, ladies and gentlemen, is your net ionic equation. So let's recap the steps that we need to take in order to construct an ionic equation. Firstly, we've got to write out the chemical equation. Remember, this chemical equation needs to be balanced, and it will be good to include the state symbols. Why? Because in step 2, we need to split up all the aqueous compounds. And to know which are the aqueous compounds, it will be good to refer to the state symbols. So in step 2, we identify the aqueous compounds in both the reactants and products, and we split up all of them into their respective ions. Thirdly, we cancel out all the spectator ions in the reactants and the products. And finally, you should be able to get your net ionic equation, which is what you want. Alright, so this concludes our video on writing ionic equations. I hope after watching this, you'll be able to construct ionic equations by yourself.